I'm here to talk to you about J.J. Thomson, the guy who discovered the electron. Joseph John Thomson, or JJ, was born in Chatham Hill, Manchester, England, so he's British. JJ studied engineering at the University of Manchester, and eventually became the Cavendish Professor of Physics at Trinity College, Cambridge. He taught many students there, including Ernest Rutherford, who would succeed him in that post, and is also quite famous in physics. Now, I had to start the story a little bit before J.J. Thomson, because I got to talk about Otto von Guericke. Otto von Guericke was famous for inventing the vacuum pump. By using this vacuum pump, scientists were able to evacuate air out of containers and allowed them to create new low air pressure environments. One thing that was immediately noticed about working in a low air environment was that electrostatic discharge would jump much further than if it was in full air. Now, as soon as that happens, they gotta go over the top, right? Okay, so in 1857, a German physicist named Heinrich Gessler sucked as much air as he could possibly out of his vacuum tube. What he found? That instead of electrostatic discharge, it became an eerie glow, similar to a neon light type of glow. And that glow was the first cathode ray. The same cathode rays that you'd find in an old CRT TV. CRT stands for cathode ray tube. This is a major invention which eventually led to modern television. Of course, with something like that produces energy, like light energy, you have to figure out how the energy is getting from one place to another, right? At this end of the tube, they have an electrode which is negatively charged. Somehow, the energy from that electrode is getting all the way over to this end of the tube where it glows. So, experiments. They decided to place all sorts of obstacles and stuff to get them around, and they figured out that it's a ray. The ray has to travel in a straight line. If there's an obstacle, ray can't get past, right? No glow. So, what are the rays made of? Is the next question. And that's where J.J. Thomson comes in. At this end he had the electrode, right? This end he had an electrometer which would measure how many cathode rays were getting to the one end. In the middle, he sets up an electromagnetic field, and he realizes that as soon as the electromagnetic field is activated, the cathode rays stop hitting this panel. And where do they go? It turns out that they're deflected by the magnetic field, which suggests to J.J. Thomson that cathode rays are negative. Next question, why? Okay, using ever more elaborate set of vacuum tubes, J.J. Thomson was able to figure out that this experiment shows that however we twist and deflect the cathode rays by magnetic forces, the negative electrification follows the same path as the rays, and that this negative electrification is indissolubly connected with the cathode rays. What this means that the negative charge and the cathode rays are one and the same, and that the rays are negatively charged and the negative charge is contained in the rays. This means that they cannot be separated as originally thought by J.J. Thomson. Or the simple version. 1. Cathode rays are negatively charged. 2. They are made of particles. 3. These particles had a mass smaller than any known atom at that point. Any known atom at this point as well. Frankly, what he had discovered was the electron. Now, discovering a particle smaller than any known at that point was not something to be taken lightly. Well, at the time, J.J. Thomson called what we now know as electrons corpuscles. J.J. Thomson also posed that these corpuscles came from within the atom. All of a sudden, we have a problem, because at the time it was believed that atoms were indivisible. If the corpuscles came from within the atom, that means that something is coming out of the atom. That means it's divisible. If the atom is divisible, that means we have to come up with a whole new model of the atom. It means that everything that was based on the original model is false. So, now the previous model was the Dalton model, also known as the billiard ball model. Pretty self-explanatory. They thought atoms were solid balls. Of course, that's not the case as we know today. So Thomson had to come up with a new model. He called it the plum pudding model. Of course, everyone else called it the Thomson model. Plum pudding model consisted of a gelatinous blob. You may have heard it called the chocolate chip cookie model or the raisin bun model, but really both those suggest static electrons. But in reality, Thomson's was very gelatinous and allowed the electrons to move freely throughout the sea of positive gelatin. So Thomson had come up with a new model and new concept of the electron, that they were made of particles. Unfortunately, we now know that neither of those are correct. You probably know from physics class that the guy who disproved Thomson's plum pudding model was Bohr, with his famous gold foil experiment. Took a few atoms thick of gold foil, shot electrons at it, and some of them went through, and some went boing. What this means is that atoms are mostly hollow and not plum pudding. Bohr's model suggested that electrons fly around the central nucleus of the atom in orbitals, which is much closer to the model that is used today. What you may not know that is a critical person in disproving that electrons were particles, and in fact a combination of particles and waves, was J.J. Thomson's own son, G.P. Thomson. Though never as famous as his father, G.P. Thomson did win the Nobel Prize for his work. Of course, J.J. Thomson had already done that years ago. If you learn anything about science, it's not being right that counts. It's helping the field as a whole. And J.J. Thomson certainly did that. He single-handedly disproved that atoms were indivisible, which is most certainly correct, as we now know about all kinds of little particles smaller than the nucleus of an atom. So what if he wasn't right? He was more right than the people before him.